Başladı. Ha, kaydediyor muyuz ya? Tamam. Kaydediyoruz. Tamam. If you don't have any more questions about the oral exams, then we can continue with our questions, our recitation questions. Do you have anything to ask related to subject or related to oral exams? No, nothing more. Okay. Now, today we are going to solve some questions about Euclidean domains and unit factorization domains. If you have any problems, please just interrupt me and ask your questions, okay? Now, firstly, I want to start with the ring of Gaussian integers. The first one, let I be an ideal, be a non-zero ideal. This is an interesting question. Non-zero ideal of the ring Zi of Gaussian integers. I think you have talked about this ring in your lecture today. Now we are going to consider a non-zero ideal of this ring, and we are going to prove that for any non-zero ideal of this ring, prove that this quotient ring, that I over I, is a finite ring. It's finite. Don't you think that this is interesting? You have an infinite ring, and for any non-zero ideal of it, the quotient is finite. I think this is interesting. Now, firstly, we need to recall something, that I, as you have done in your lecture today, is a Euclidean domain. Euclidean domain with a norm function n from Zi to non-negative integers, taking a plus bi, let me call this alpha, to alpha times alpha conjugate, which is actually a plus bi times a minus bi, and this is nothing but a squared plus b squared. You're just taking the coefficients of your elements alpha and square them, and then just add them up, okay? With this function, we know that I is a Euclidean domain. Euclidean domain means that you can divide, and you can divide properly, okay? Like you can consider when you are talking about Euclidean domains, you can also have polynomials in your mind, okay? They're very similar. If you know how to apply division of polynomials or two integers, then the idea behind the Euclidean domain is just the same, okay? You have some elements from the ring, and you want to divide one by another, and you want to use just this function, okay? You want to relate your division with this function. Actually, this is called somewhere as norm function or Euclidean function. Actually, if you're talking about Euclidean domains, then this is called as Euclidean function. Euclidean function or Euclidean valuation. Okay, just keep division in integers or in polynomials while you're considering the Euclidean domain. Okay, for example, if you, okay, as a note, just as a basic example, consider Z with the usual division. Usual division, no. You're applying usual division, and as the Euclidean function, you're going to use absolute value. With absolute value, okay? What are you saying when you're dividing, for example, a by b, divide a by b, or x by y, whatever, x by y, then you're saying that over integers, oh, I'm so sorry. Okay, over integers, we are saying that there exists q and r in z, such that x can be written as y times q plus r, where r is some integer strictly less than x and greater than or equal to 0. Okay, you're just okay, if we are considering this as integers, we need to use absolute values here. Absolute value of r is positive. Maybe this is better. Absolute value of r is strictly less than x, or r is equal to 0. Okay?
Cam y olacak sanırım ama.
Y, yeah, of course. We are dividing x by y, of course. The quotient we are talking about. So this is just the usual division over integers, and apply the same idea to an abstract Euclidean domain. Okay? So now we know that for our question that I is the Euclidean domain, and let us take a non-zero ideal of it. Let I be a non-zero ideal of Zi. Now, what can you say about this ideal? Do you have any characteristic property for this ideal?
Principle.
Sorry?
Principle.
It is principle. Why is that so?
Because it's a PID.
That I is a PID.
That
every Euclidean domain is a PID. Then this ideal has to be generated by just one element. So it is principle. As every Euclidean domain is a PID, that I is a PID, and I is principle. So what we know, so there exists alpha in that I, such that I is generated by this alpha, right? Okay, so let us take an arbitrary element from this quotient ring. Let a plus bi plus I from this quotient be an arbitrary element. Be arbitrary. Okay. So we need to find all possible values for this A and for this B right now, right? Okay, we have a generator here, and we are in a Euclidean domain, so actually we can divide this A plus bi, this arbitrary representative of coset, by our generator alpha, right? So apply division or divide A plus bi by alpha, which is possible as Zi is a Euclidean domain. Okay. So what we have there exists Q R in Zi such that A plus bi is equal to alpha times Q plus R, where R is equal to 0, or this function value of R is strictly less than function value of alpha. Okay, we have two possibilities. So from here, using this equality, what we have A plus bi minus R is a multiple of alpha. And we know that alpha is the generator of I, so this means that this right-hand side lies in the ideal I, because this is generated by alpha. So this means that the difference of these two elements, a plus b, I and r, lies in I means that they represent the same coset, right? So a plus bi plus I is equal to r plus I. Okay. So instead of an arbitrary representative for the coset, we can actually use its remainder by dividing our representative by alpha. Okay. So this means that it is enough to determine all elements in Gaussian integers in this ring Zi whose norm is less than this given norm. Okay, the norm of alpha. Okay, so it is enough to count all elements R with an R is less than an alpha. So this means that this R actually does not depend on this representative a plus bi, but it is bounded, its norm is bounded by the norm of the generator. Okay? And for when you fix the non-zero ideal, then it's you can also fix a generator for it. So this n alpha can be considered a fixed number. Okay? So if let's R be an element of x plus yi. So this norm of R is nothing but x squared plus y squared, or instead of this one, let me first write x plus yi, x minus yi, which is x squared plus y squared. So this means that we are looking for all x and y values such that x squared plus y squared is strictly less than n of alpha. So find values x and y in Z such that x squared plus y squared is less than an alpha. Actually, this is a set of two tuples consisting of all integer tuples x and y inside a circle whose radius is n of alpha, right? And we have only finitely many such tuples. So this means that there are only finitely many integers satisfying x squared plus y squared is less than n alpha. Let me also draw my interpretation here. We have a circle of radius and alpha, actually, okay? We know that these are positive numbers or non-negative numbers. And since we know that I is non-zero, alpha is non-zero, I non-zero means that alpha is non-zero. This is generated by alpha. Okay, so actually we are looking for all integer tuples here, right? Inside this ne bunun adı ya? Circle mı? Circle. Yes, circle. Circle of radius and alpha. So we have only finitely many this two tuples. Okay, so this means that hence that I over I is finite. Okay? Any questions? No. Okay. Now is the second question. This is something I'm always confused. Confused about what? Confused about this one. We have Euclidean domains. and we have Euclidean functions of them on them. But somewhere we have some rings, some integral domains, and we have some functions of them on them, which are very similar to a Euclidean function, but they're not Euclidean functions for those rings. Okay, I'm going to give the example for this one. This is the second question. Let n. We are going to talk about some special rings here. Let n be a square-free integer. Now consider the ring Z root n, which consists of all elements of the form a plus b root n, where a, b are integers. Okay, now check that this ring, actually you can directly say it, I think. This one is an integral domain. Can you directly say that? That these rings are all integral domains for any n? Can you say it directly? Any idea? How can you say, by just saying just one thing, that these rings for every n, these are integral domains? Beni duyuyor musun? Ha belki de beni duymuyorsunuz.
Duyuyorum.
Z integral domain olduğu için mi hocam?
Efendim?
Z integral domain olduğu için mi?
No.
Principal ideal domain olduğu için mi?
Principal ideal domain olduğunu nereden biliyorsun ya?
Salladım hocam.
Anladın mı? Ki zaten the reason is not that that is an integral domain or these z root n's are principal ideal domains, because we cannot be sure that these rings z root n's are principal ideal domains. For example, for n is equal to 5, these are not PID. Okay, so we cannot say that, but we can say directly that since these rings are subrings of complex numbers, and we know that complex numbers are complex numbers form an integral domain. Actually, they are field. It is a field. So since this is an integral domain, this is an integral domain, right? Subring of an integral domain is integral domain, right? So this means that this is a field and hence integral domain as a subring of an integral domain Z root n, and it's square-free integer, okay, is an integral domain. You can say directly like this one. Okay, is it clear? Okay, but the thing that we are going to show in this question, first we are going to define a function on these rings, n from z root n to z, okay, taking a plus b root n to, actually this one, a plus b root n times a minus b root n. This is the general form. You can see this norm in any textbook. And this is a squared minus nb squared, okay? With this function, we have some good properties. The first one, we are going to prove that let x be an element from this ring, then prove that this norm the function value of this x is equal to 0 if and only if the element is 0. Secondly, let x and y be two elements from this ring, this special ring, this one. Now prove that this is multiplicative and xy is equal to an x times ny. And lastly, prove that and x is equal to plus minus 1 if and only if x is a unit of this ring. Okay, this means the unit ring. Okay, so actually, if you consider Gaussian integers, this function is nothing but its norm, right? Euclidean norm. It's Euclidean valuation. But for an arbitrary integral domain, you can also define such a function. But by defining such a function does not mean that your ring is actually a Euclidean domain. Okay? Do not mix these things up. Okay? This is one of the subjects that I'm very confused with. But I'm trying to understand. Okay?
Hocam bir daha söyleyebilir misiniz?
Şunu söylüyorum. Diyorum ki ZI'de de mesela bu fonksiyonun aynısı vardı ZI'nin üstünde ve bu fonksiyonun aynısıyla ZI Euclidean domain oluyordu. Ama biz bu fonksiyonu ZI'ye çok benzeyen ringlerin üstüne de koyabiliriz ve bu fonksiyon o ringlerin üstüne çok güzel özellikler sağlatır. Ama bu demek değildir ki sen bu Z köken ringinin üstüne böyle bir fonksiyon koyabiliyorsun diye Z köken ringi Euclidean domain olmak zorunda değildir.
Hocam zaten benim bu fonksiyonumun Z plus'a gitmesi lazım değil mi?
Z plus'a da gitme. Al sana Z plus'a gönderelim. Hala değildir.
Ha tamam.
Tamam mı?
Tamam.
Olmak zorunda değil yani. Bunlar bu fonksiyonlarla with functions like this one, actually if n is equal to -1, which gives us the Gaussian integers, if n is equal to -2, +2, 3 becomes all becomes Euclidean domains. But for example, if you consider plus or -5 instead of this n with this function, it is not a Euclidean domain. Or I think, if I'm not mistaken, if you put -6 instead of this n, it is not again a Euclidean domain. Okay, so seeing such a function shouldn't lead you to the fact that this ring being a Euclidean domain directly. Okay, be careful about that. Okay, what does it mean for the first one? I'm not going to do the second one. It is just calculation. Okay, you are going to do that. So for the first one, the second one, exercise, just calculation. Okay, the first one. Let x be an element from the ring. Now the first side, this part is okay. This one, this part. If x is 0, then its norm is 0. If x is equal to 0, then actually we can write x as 0 plus 0 root n. Then this n of x is equal to 0 squared plus root n times plus minus. This is minus n times 0 squared. This is 0. This is trivial. The other side, if n of x is equal to 0 for x is equal to a plus b root n, let me say, then this means that a squared plus b squared, a squared minus, okay, and b squared is equal to 0. Okay. Now from here, we are going to evaluate every case where first b is equal to 0. If b is equal to 0, then a has to be equal to 0 because we have a squared minus n times 0 is equal to 0. So from here, a becomes 0 since we are doing this calculations over z. Okay. Then if b is not equal to 0, then this means that we have this equality and b squared is equal to 0. From here, n becomes a squared over b squared, and this is nothing but the square of something, right? But in the question, it is given that n is a square-free integer. This means that it does not contain the square of any integer. So this means that this cannot be the case. This is not the case as n is a square-free integer. So this means that b cannot be equal to 0. B has to be equal to 0. So a has to be equal to 0. So a is equal to b is equal to 0 and x is equal to 0. So if the norm function value of an element is equal to 0, then this means that that element has to be equal to the 0 element. Okay? So what about the third one? Third one asks us to prove that if the function value of an element is plus or minus 1, this means that this element is a unit element, okay? It has a multiplicative inverse and vice versa. Okay. So let's let x be equal to a plus b root n.
Hocam square free demek bir integer'ın karesi olmamak demek değil mi?
İçinde hiç kare olmaması demek. Sallıyor muyum?
A bölü B mesela şeyse 1 bölü 2 ise o zaman n zaten integer değil.
Aha.
Tamam pardon.
Yok ama içinde şey olmaması demek. Square free demek bence bence ne demekse onu da bilmiyorum da ben hep 10 senedir falan square free demek içinde hiçbir şeyin karesi yok demek bence. Hala ben. Yoksa şey derdi. Öyle olmasaydı n bir şeyin karesi değil derdi. İçinde hiç kare yok demek istiyor burada.
Evet square free evet içinde kare yok
Ama
demek evet
içinde
hocam.
kare yok. Tamam. Şimdi bir tane we have taken an x a plus b root n. Now I'm going to use if and only if statements here. If norm of x is plus or minus. I think you have done this. You did this in your lecture today. I'm not sure. Over goes in integers, I guess. Now this is if and only if. What is norm? This is a plus b root n times a minus b root n, which is a squared minus, okay, we should say plus 1 if we use absolute value. Plus 1, just 1. Okay, a squared minus nb squared. This is equal to 1. Okay. No. What is norm? Okay. And x is equal to just this one. B root n times a minus b root n, and it is given as 1 here, n of x. And here, what you have, your element a plus b root n, a multiple of your element is 1. This means that a plus b root n, which is x, divides 1. And divides 1 means that it is an invertible element, right? This is if and only if x divides 1, And this implies that this is again if and only if x is an element which has a multiplicative inverse. Okay? Yes. So in such rings, if you use such a function, if you use such a function, then you know that the function value of 0 is 0. And you know that these functions are multiplicative over these rings. And you can find actually units of such rings easily by just looking at its norms, its their function values. Okay? So by using this one, we are going to show that a ring like this one, z root something, is not a Euclidean domain, is not a UFD. Actually, at the end, it is not a Euclidean domain. If it is not a UFD, then it cannot be a Euclidean domain, right? So let us consider the ring as the third question, I guess. Prove that. Bunu da kullanmayacakmışım ya. Şunu da kullanacakmışım. Tamam. Prove that z root -5 is not a, which one do you prefer? Is not a UFD or is not a Euclidean domain? Which question do you prefer? The solution is just the same. UFD. At the end, we can conclude that since this is not a UFD, it cannot be a PID, so it cannot be a Euclidean domain because we know that every Euclidean domain is a PID and every PID is a UFD. So this means that not a UFD, then not a PID, just taking the contrapositive, not Euclidean domain. So if we can show that this z root -5 is not a UFD, then we can conclude that it cannot be a Euclidean domain, okay? Okay, now for this one, I'm going to use the function that we have talked in the previous question, okay? So consider the function n from z root -5 to z positive. Did you define this function from non-zero elements of the ring to non-negative integers, or what? Is 0 included here or not? Is 0 included in the domain or not?
Not included.
Yok hocam.
Not included. Okay. -0 to z positive or non-negative?
Union 0 demişti hocam ama.
Okay. Then non-negative. Greater than or equal to 0. Okay. So we are taking a plus b root -5 to a plus b root -5 times a minus b root -5. And this gives us a squared plus 5b squared. Now we don't have to use absolute values because they are always non-negative integers, okay? Since we are adding squares of something, okay? So now here, this is not a UFD, means that we need to find two different non-trivial factorization for a given element, okay? So for this one, let us consider the element 9 inside this ring. Consider 9 in z root -5. Can you see two non-trivial factorization of this element 9 inside this ring, of course? First one, the easy one, we can write this one as 3 times 3, right? The other one, can you see it?
2 plus square root of minus 5 and 2 minus square root of minus 5.
2 plus square root of minus 5 and 2 minus square root of minus 5. So we have right some factorizations of 9. Okay. Now, if we can show that these elements seen in these factorizations are irreducible elements, then this means that you have found two non-trivial factorizations. Okay. If one divides the other one, then these two does not mean that you have two different factorizations. Okay. But if you can show that these elements 3, 2 plus minus root minus 5 are all irreducible elements, then this concludes you to the fact that this 9 can be factorized non-trivially into two different ways. Okay. So now our claim.
Hocam birbirlerinin associate'leri değil demekle her biri irreducible demek aynı şey olacak değil mi?
Sure. Claim actually 3, 2 plus root minus 5 and 2 minus root minus 5 are irreducible. Okay. Now for this one, actually we are going to prove something more general. Instead of this one, we are going to show that an element inside this ring of norm of function value 9 has to be an irreducible element. Okay? Yes. So more generally, specific to this ring, specific to this ring, we are going to prove that. For alpha in this ring with norm of alpha is equal to 9, alpha is irreducible. Okay? So let alpha be an element of with norm of alpha is equal to 9. Suppose that we have a factorization of this alpha. Suppose alpha have some factorization beta times gamma. Okay, now you're going to prove that this function is multiplicative, right? So if you take the norms of both sides, norm of beta times gamma, then what you have, we have norm of beta times norm of gamma. And we know that this is 9. So what are the possibilities for norm of beta and norm of gamma? Norm of beta may be 1. These are integers. These are positive integers. So n of beta may be 1, 3, or 9. Okay? If norm of beta is 1, is equal to 1, then this means that beta is a unit. By previous question, last part. Okay? Now, if n of beta is equal to 3, then for beta is equal to a plus b root minus 5, n of beta is equal to a squared plus 5b squared is equal to 3. But is it possible over z? You have square of something plus 5 times square of something is equal to 3. Is it possible? No, it is not possible, right? Which is not possible in z. So n of beta cannot be equal to 3. So lastly, if n of beta is equal to 9, then this means that n of gamma is equal to 1, and so gamma is the unit. So in the beginning, you have taken a factorization of this alpha, but at the end, one case, you have the conclusion that one of the factors has to be a unit, and in the last case, you have concluded that gamma, the other factor, has to be a unit, and in the second case, you have nothing. So this means that alpha cannot have a trivial factorization. Okay. So either beta or gamma is a unit, hence alpha is an irreducible element in set root minus 5. Okay, if you consider our elements, we were doing this because we need to show that these elements are irreducible. If you look at the norms of these elements, they all have norm 9. Okay? So since norm of 3 is equal to norm of 2 plus minus root minus 5 are all 9, this means that these are all irreducible elements. 3, 2 plus minus root minus 5 are all irreducible elements. Okay, so this means that we have found two different non-trivial factorizations of 9. So this means that this ring cannot be a unique factorization domain because you cannot factorize an element uniquely in this case. Okay, so the factorizations. Nine, 3 times 3, and 2 plus root minus 5, 2 minus root minus 5 are not unique. This ring is not a unique factorization domain. So this means that z root minus 5 is not a PID and hence not a Euclidean domain. Okay, so this means that you cannot find a Euclidean function on this ring. Okay. Question? Anything not clear? No.
Sorumuz daha var. Bugün ne kadar sürecek acaba?
Bir sorum daha var. Bir soru daha çözeceğim. Ondan sonra bitecek.
Tamam.
Hocam biz şimdi 9'u parçaladık ama sadece konjüge cinsinden parçaladık ya.
Konjüge cinsinden demek ne demek?
Ya a artı b kök eksi 5, a eksi b kök eksi 5.
Evet.
Başka türlü bir şekilde çarpımı olamayacağını nereden biliyoruz?
Olabilir işte. Bak yazdık başka türlü bir çarpımını. 3 çarpı 3 diye yazdık mesela. Böyle yazdık bir de. İki farklı şekilde yazdığımız için zaten unique factorization domain olamaz.
Ha, bunlara bakmam yeterli. Pardon.
Evet evet. Aha. Ve şu anda işte bunların irreducible olduğunu söyleyerek ne söylemiş olduk? Bu factorization'lar birbirlerinin aynısı değil. Yani birbirlerinin aynısı demek ne demek? Şimdi bir yerde yazdım. Bir elemanı you have written an element as a product of irreducible up to associate, right? And at the other side, you have written the same element as a product of irreducible up to associate. But if you compare the irreducible elements, they have to be the associates of each other in a Euclidean domain, in a unique factorization domain. But here, we are in a situation that we have two different factorizations into irreducible, and they are not associates of each other. Okay? So this contradicts with the unique factorization here. Okay? It doesn't matter whether you use conjugate of the same element or not. Okay? I think you were talking about these two, and you're talking the second one is the conjugate of the first one. It is okay. Okay? The problem is that are both of them irreducible or not? Okay? These were the questions to show that this ring is not a unique factorization domain. That this factorization is not unique.
Eğer irreducible olsalardı da 3 çarpı 3 yani 3'ten sağ taraftakiler 3 ile associate değil mi ona bakacaktık değil mi?
Yes, sure.
Orada da associate olmasaydı yine unique factorization domain değildi diyecektik.
Yes.
Ama irreducible olmadığı için direkt unique factorization domain değil dedik.
Irreducible, bu elemanların hepsi irreducible olduğu için unique factorization domain demek. Yani farklı irreducible'larla sen aynı elemanı yazabildiğin için unique factorization domain olmadı.
Associate olmayan farklı irreducible. Tamam.
Tamam.
Ben bir şey sorabilir miyim hocam?
Evet.
Hepsinin teker teker irreducible olmalarından ya da teker tekeri çok önemli değil de irreducible olmalarından nasıl associate olmadıklarına vardık? Ben orayı kaçırdım.
Düşünüyorum. Hepsinin irreducible olmalarından nasıl associate olmadıklarına vardır. Onu ben çok seviyormuş gibi hiç düşünmemişim. Bakalım, düşünelim. Hepsinin irreducible olması önemli. Şöyle, şimdi bunların biz irreducible olduklarını söyledik. O zaman bunların associate olmaları demek ne demek?
Bir unitle çarparak diğerini elde edebiliyorum ben.
Bir unitle çarparak diğerini elde edebiliyorum demek. Peki bu ringin unitleri neler? Nx eşittir
Artı eksi 1 sadece.
x eşittir a artı b i dersen nx dediğin şey şu olsun. Z eksi 5 var. O zaman norm x dediğimiz şey ne olacak? A kare artı 5 b kare. Dolayısıyla buradan neye vardık? Bunun 1 olması demek sadece a kare eşittir 1 olursa mümkün olur. Burada da a eşittir artı eksi a kare eşittir 1 ve b eşittir 0 olursa mümkün olur. Dolayısıyla x dediğin şey artı eksi 1 olabilir sadece. O zaman buradan vardığın şey ne? Buradan vardığın şey bunların associate olmamaları. If 3 and 2 plus minus root minus 5 are associates, then 3 is equal to plus minus 2 plus minus olmalıydı. Ama bu doğru değil mi? Bu ringin şeylerinin unitlerinin sadece 1 ve artı eksi 1 olmasından geliyormuş kolay bir şekilde associate olmamaları.
Teşekkür ederim hocam.
Belki teşekkür ederim. Belki söyleyeyim. Okay. Using norm is kind of confusing. But in our last question, we are going to just apply direct computation to show that an element is not prime and an element is irreducible. Okay. I think this is fourth question. Prove that. That root 5 now, not minus 5, just 5, is not a unique factorization domain. Okay? Now, for this question, we are not going to find a non-trivial factorization for an element, but we are going to show this one, that root 5 not being a UFD, by showing that we have an irreducible element in the ring, which is not a prime element. Okay? You know that after PID, you know that everything is everything. Okay? But here, to show that a ring is not a UFD, it is enough to find a prime, to find an irreducible element which is not prime. Okay? Because you know that in UFD, every prime is irreducible and every irreducible is prime. Okay? Now for the first one, we are going to show that 1 plus root 5 is not a prime element inside this ring. And secondly, we are going to show that 1 plus root 5 is irreducible.
Hocam böyle not PID olduğunu göstermiş olmuyor muyum sadece?
Not PID mi? Yo, niye ki? UFD'lerde de bütün prime'lar irreducible, bütün irreducible'lar prime. Değil mi? Değil mi? PID, şimdi, you have seen this theorem as if R is a PID, then every irreducible is prime, right? This is the statement. Am I wrong?
Evet.
So this means that you can actually take this one to one step further and you can restate the theorem as a different version. If R is a UFD, then every irreducible is prime, right?
Doğru, tamam. Çünkü hepsi PID'ler UFD.
Yes, every
Tamam.
PID is a UFD, so you can just move it to the UFD case. So
Doğru.
if this question were asking to show that root 5 is not a PID, then you can use the same argument. Okay, because you know that every PID is a UFD, so every fact that applies in a PID also applies in a UFD. So you can use the facts in both positions. Okay, so for the first one, what we know, we can write actually 4 as 1 plus root minus 5, 4 or minus 4. Minus 4 is better. And 1 minus root minus 5, and you can also factorize this one as 2 times minus 2. Now what is it?
Hocam.
Yes.
Neden root minus 5 dedik?
Ay 5. Teşekkür ederim. Deminki soruda kalmış aklım. 5. O 6 yapar zaten demin yapmak için. Burası 5 oldu. Tamam. Şimdi diyorum ki bir factorization'ın one side of the equality we have 2 and in the other side we have 1 plus root 5. If 1 plus root 5 divides 2, then this means that a multiple of 1 plus root 5, a plus b root 5, has to be equal to 2. Can it be? Just apply the multiplication. We have a plus 5b plus a plus b root 5 is equal to 2. So from here, we have a plus b root 5b is equal to 2, and a plus b is equal to 0. We need to solve these two together. From here, what we have b is equal to 1 over 2. This is not an integer, so this cannot be the case. Okay, what if cannot happen? What if the same thing, 1 plus root 5 divides the other factor, minus 2. For primes, we are looking these ones. Then the same idea, root 5 times a plus b root 5 is equal to minus 2. And here, a plus 5b is equal to minus 2. And a plus b is equal to 0. Solve them together. Minus, we have b is equal to minus 1 over 2. Now, this is not an integer, so it cannot happen. So actually, what you have here, you have your element 1 plus root 5 divide the product of two elements, but it does not divide any of the factors. So this cannot be a prime element, okay? Although 1 plus root 5 divides x times y here. Here x is 2 and y is minus 2. 1 plus root 5 does not divide x, and 1 plus root 5 does not divide y. This means that 1 plus root 5 is not prime. Okay? What about irreducibility? The second part, 1 plus root 5 is irreducible. Okay, what we have, okay, what was the norm? Norm was this one. Norm of 1 plus root 5, this is öyle mi yapsam? Öyle yapmayayım, şöyle yapayım. 4 is equal to 1 plus root 5. Norm'u kullanmak istiyorum. Okay. We were trying to show that this element is irreducible. So suppose to the contrary, 1 plus root 5 can be written as x times y. Okay. Kafam karıştı. Niye çalışmadı kafam? Niye çalışmadı? Okay. So, take the norms of both sides. Root 5 is equal to norm of x times y, which is norm of x times norm of y. What was the norm of this element? 1 plus root 5 times 1 minus root 5, which is equal to, we have used the absolute value. This is 4. We have n times x, n of x times n of y. Okay. Okay. As we have taken, suppose to the contrary dersem netleşecek. Contrary, that we have taken a non-trivial factorization of 1 plus root 5. This means that n of x and n of y is not equal to 1. And since the product of this n of x and n of y is equal to 4, these two has to be equal to 2, right? Okay. Now try to solve the equation inside ring of integers. Now let's x is equal to a plus b root 5, and we have shown that n of x is equal to 2. So what is the norm in terms of a and b? We have a squared, okay, a squared minus 5b squared. Now this is equal to 2, means that we need to solve a squared minus 5b squared is equal to 2, and or a squared plus 5b squared is equal to minus 2. In each case, we are going to obtain the same result. So I'm just going to solve one part. Okay. Just separate the cases where A is an even number, A even integer, B is an even integer, A is even and B is odd, both is even and both is odd. Okay. So the first part, if A is 2k and B is 2j plus 1, then we have, I'm not going to do all of the calculations here, but just going to write the result. This is nothing but 4k squared minus this one minus 20j minus 5. This is an odd number, so cannot be equal to plus or minus 2, right? So if the second case, A is equal to an odd integer and B is an even integer, then we have this one as 4k squared plus 4k plus 1 minus this one. This is again odd, so cannot be equal to plus minus 2. The other case, if this is even and this is even. Now, if you look at this one, you have a multiple of 4. What was it? 4k squared minus 20j squared. This is a multiple of 4. So cannot be equal to plus or minus 2. And lastly, the same thing here. 2k plus 1, odd, b is equal to 2j plus 1. Then a squared minus 5b squared is equal to, again, the same idea for k squared. I'm writing this one if you want to check something. And j squared minus 20j minus 4. This is again a multiple of 4. So this cannot be equal to plus minus 2. So in every case, neither of the cases, we cannot have the norm of x is equal to plus or minus 2. So this means that we cannot have such a non-trivial factorization. Okay. So we cannot have a non-trivial factorization of 1 plus root 5, hence 1 plus root 5 is irreducible. So in our ring, we have an irreducible element, which is not prime. This means that this ring cannot be a unit factorization domain. since in Z root 5 there is an irreducible element which is not prime, Z root 5 is not a unique factorization domain. Okay, this is another way to show that a ring is not a unique factorization domain. In the first question, we have showed that Z root minus 5 is not a unique factorization domain by finding explicit factorization, non-trivial factorization of an element inside the ring. But now we have used a theorem saying that in unique factorization domains, every irreducible element is prime. But in this ring, we have found an irreducible element which is not prime. So this means that this ring cannot be a unique factorization domain. Okay?
Hocam,
Yes.
Ben yine aynı soruyu soracağım da tam anlayamadım. Şimdi prime'sa irreducible'sa prime,
Evet.
principal ideal domain için doğru bir cümle.
Evet. Principal ideal domain için doğru olan bütün cümleler UFD'ler için de doğrudur. Ama UFD'ler için doğru olup principal ideal domainler için doğru olmayan cümleler vardır. Şimdi şu var ya elimizde. Bütün şunu düşün. Şimdi bütün Euclidean domainler PID değil mi?
Evet.
PID'lerde UFD. Şimdi o zaman sen bir tane ring, yani Euclidean domainlerden bahsediyor. O de ki Euclidean domain ise eğer şu doğrudur. O zaman UFD ise de o doğrudur. Çünkü sen biliyorsun ki Euclidean domain olan her şey UFD'dir. Ben bir şey yanlış mı anlıyorum, yanlış mı söylüyorum?
Yani bu cümle doğru değilse PID değil diyorum. PID değil deyince UFD değil diyemiyorum ama.
Hayır, olmaz öyle. UFD değilse PID değil diyebilirsin. PID değilse
Evet.
UFD olabilir çünkü hala.
Ben bunu hocam biraz anlamaya çalışayım. Anlayamazsam tekrar sorayım.
Tamam.
Hocam galiba ben de aynı yerde takıldım. Şimdi burada şey dedik ya, irreducible ama prime değil.
Yanlış bir şey de söylemiş olabilirim. Evet. Şimdi UFD'lerde şu doğru değil mi? Bütün irreducible'lar prime. In a UFD, every irreducible element is prime. Is this true?
Every PID'de o göstermiştik onu sadece.
Ben yanlış mı biliyorum? Öyle
Ya bizim derste gördüğümüz şey, ben de yanlış bilmiyorsam, PID ise irreducible ve prime aynı şey.
UFD ise benim bildiğim şey de UFD ise öyle. UFD ise de öyle.
Ha, ben şeyi soracağım. Eğer PID'de bu doğruysa UFD'de de doğru.
Tamam. Herkes sorusunu toparlasın. Ben de anlamıyorum herhalde bir şey. Yanlış bir şey de söylediysem Allah vallahi yandık abi. Bir de kayıt aldım.
Hocam siz şimdi bu soruyu UFD'de bu cümle doğru. Bu
Evet.
cümle doğru değilse UFD değil dedik değil mi?
Evet, UFD'de bu cümlenin doğru olduğunu biliyorum ben. Şimdi onu kontrol edeceğim. Acaba tövbe estağfurullah yanlış mı biliyorum 30 yaşında diye.
Hayır, belki doğru biliyorsunuzdur da biz daha o kısmı görmemişizdir ama sadece PID'de doğru olduğunu bilerek UFD'de de doğru olduğunu.
Hayır. PID'de doğru olan
UFD'de doğru olmak zorunda değil. Değil mi?
PID'de doğru olan UFD'de her
Çünkü ben UFD'de
UFD'de
doğru olmasını istiyorsam
Hı hı.
PID'den göstereceksem UFD PID diyeceğim, ondan sonra doğru olduğunu göstereceğim değil mi?
UFD PID diyeceğim ne demek? Anlamadım.
Yani PID'de kanıtladım ben bir şeyi. UFD'de sadece bu gerçeği kullanarak doğru olduğunu göstermek istiyorsam UFD ise PID'nin doğruluğuna ihtiyacım var değil mi? Sadece oradan onu kullanacaksam yani.
Anlamıyorum, özür dilerim, anlamıyorum ya. Gel söyler misin?
Şimdi ben PID'de bir cümlenin doğru olduğunu biliyorum.
Evet.
PID ise UFD olduğunu biliyorum.
Evet.
Ama bu PID'de doğru olan cümlenin UFD'de de doğru olduğunu göstermez değil mi?
Şimdi her PID UFD ise o zaman PID'lerin bütün özelliklerini UFD'ler hayır. Demek istediğini anladım. PID olmayan UFD'ler var. O yüzden diyorsun ki PID'lerde doğru olan her şey UFD'lerde doğru olmayabilir. Doğru mu anlıyorum seni?
Evet. Yani UFD PID'yi göstermiyorsa
Tamam. Düşünüyorum. Evet, PID, UFD. Yine bu 10. Tam direkt search yapacağım. Bir bakalım. UFD.
Evet hocam, dediğiniz gibi yani PID olmayıp UFD olanlar da var. ZX örneği mesela.
Evet,
Yani PID'de dediklerimiz doğru. Aynen UFD'de o özellikleri taşımak zorunda değil.
tamam. Şuna bakıyorum o zaman. O zaman bu dediğimiz şey UFD'de doğru mu ona bakalım. PID'de doğru olan bir şey. UFD'lerin hepsi için doğru olmak zorunda değil. PID every prime irreducible. Tamam. Eğer tutuyorum. Every irreducible prime UFD. Ama PID ise. Ha UFD'lerde de aynı.
Hocam Malik'in kitabında bir teorem belirtilmiş. Yine unique factorization domain every irreducible element is prime demiş sadece.
Evet.
Bunu göstermemiş.
Ya evet yok bu şeyde de doğruymuş. Ya benim zaten kafamda kalan şey şu büyük ihtimalle. Ben bunu birazcık zayıfım bu konuda fark etmişsinizdir zaten. Bir yerden sonra o işte PID'den sonra her şey oluyor. Hiçbir ayrım kalmıyor. O zamana kadar yaptığımız hiçbir ayrım kalmıyor. İşte öyle olunca ben bunu da yapmışsınızdır diye düşünmüşüm herhalde. O yüzden doğal bir şekilde kullanmışım ama soru evet kafamı karıştırdı benim. Normalde evet PID'lerde sağlanıp UFD'lerde sağlanmayan özellikler
hocam irreducible elementin prime olduğu PID'den bağımsız da doğru.
yok o doğru. Ben sadece senin soruna cevap vermek istiyorum. Onu not edelim buraya.
Yani bu soruda aslında biz sadece o kısımdan bir çelişki bulmuş olduk değil mi? Irreducible dedik. Prime olmadığını gösterdik.
Evet. Ama buradan işte ben şeyi söylemedim. Irreducible ama prime değil. Dolayısıyla bu PID değildir. Dolayısıyla UFD değildir demedim. Ben direkt şunu kullandım. UFD'lerde irreducible'lar prime'dır. Ben şimdi irreducible buldum. Prime olmayan. O zaman dedim ki bu UFD olamaz. Çünkü bu statement UFD'lerde doğru. Şimdi benim kafama takılan senin sorduğun diğer şey. PID'lerde sağlanan her şey UFD'lerde sağlanmak zorunda mı değil mi? Değil. Cevabımız değil. Ama neden değil? Ona mesela işte bir tane bulalım. Örnek bulalım. PID'lerde sağlansın ama UFD'lerde sağlanmasın.
Hocam ama her PID bir UFD değil mi?
İşte PID olmayan bir UFD istiyorum senden. ZX mesela. ZX'te sağlanan ZX'te yok. Z'de sağlanıp ZX'te sağlanmayan bir şey mesela. Z çünkü PID. PID'den dolayı UFD. Ama ZX UFD PID değil. İşte o yüzden şu anda aradığımız şey şu. Öyle bir özellik arıyoruz ki Z'de sağlansın. Z'in PID olarak sağladığı bir şey. Dolayısıyla UFD olarak sağladığı bir şey. Ama ZX sağlamasın. Çünkü ZX UFD PID olmayan bir UFD. Böyle bir özellik. Acaba var mı? Ya da işte non-trivial bir şey mi? Onu da bilmiyorum da. Soruya
Hocam, yanlış anlamış olabilirim ama şimdi sizin bu dediğiniz şey değil mi? UFD'de sağlanacak bir özellik ama PID'de sağlanmayacak bir özellik.
evet.
Ama bizim baktığımız şey tam tersi değil miydi? PID'de sağlanacak ama UFD'de sağlanmayacak. Ya ben şey diye düşünüyorum. PID'de sağlanacak ama UFD'de sağlanmayacak bir özellik
Evet,
olamaz.
onu PID'de sağlanacak ama UFD'de sağlanmayacak bir özellik olabilir. Hemen söylüyorum. PID'de bütün ideal'lar principal'dır. UFD'lerde bütün ideal'lar principal olmak zorunda değildir. Mesela ZX. Değil mi? Demin arıyorduk ya Z'de sağlanan ama ZX'te sağlanmayan bir özellik. Ideal'ların principal olması. Z'in bütün ideal'ları principal. Z UFD. Principal ideal domain'den principal ideal domain olmasından dolayı UFD. Bütün ideal'ları principal. ZX de UFD ama principal ideal domain değil. Al işte bak PID'de sağlanan ama UFD'de sağlanmayan bir özellik tanımı yani. Oldu mu? İlk başta kim sormuştu bu soruyu? Unuttum şimdi, özür dilerim. Kafam da çok karıştı zaten. Ama teşekkür ederim. ZX is a UFD.
Hocam şimdi sorunu çözdük değil mi? Benim kafam karıştı.
Furkan çözdük. Şimdi
Ha, tamam.
which is not a PID. Which şöyle diyelim. A property which is satisfied in a PID but not in a UFD. Soru buydu değil mi Furkan? Şöyle bir şey arıyorduk. Ya PID'de sağlanan her şey UFD'de sağlanmak zorunda değil. Konumuz buydu değil mi?
Evet.
Tamam. İşte bu özellik ne? PID'lerde bütün ideal'ların principal olması ama UFD'lerde olmak zorunda olmaması. Bu şey. Dolayısıyla şuna bakıyoruz. The ideal generated by x and 2 is not principal in ZX. Being principal is a property only in PID. ZX is the unique factorization domain which is not a PID. So an ideal of it, which is ideal generated by x and 2, is not a principal ideal. Okay, although it is a unique factorization domain. So not every property satisfied in PID has to be satisfied in UFD. Furkan birazdan karıştı kafan.
Yok oldu. O zaman bu UFD olmadığını.
Tamam, ben bunu şu fact'i bildiğinizi düşünerek çözmüşüm bu soruyu. O yüzden özür dilerim. Ben bunu bildiğinizi düşünmüştüm.
Ha, tamam hocam.
Tamam, yani ben şunu yapmadım. In this question I didn't do something like this. The following sentence. In this question we have shown that we have found an irreducible element which is not prime. Okay? I didn't say that since we have an irreducible element which is not prime. This ring is not a PID, so it is not a UFD. I didn't say that, okay? I thought that you know the fact, the very same fact also holds in UFDs. In a UFD, every irreducible element is prime. So I have used this fact, okay? So, and then we have discussed about something that is every property satisfied in a PID also satisfied in a UFD? And the answer is no. We have found a property of a PID which is not satisfied in a UFD. Okay? So if you have a fact stated as in a PID, it does not mean that that fact is also satisfied in a UFD. Okay? This is the summary that what we have talked in Turkish in last 10 minutes. Okay? Are we clear now?
Ben şahsen clear'ım hocam.
Okay, I am clear too. Thank you for this excellent question. I haven't thought about it till today. Okay, any other questions or comments or something to correct me? Okay, if not, then good luck with your exam on Friday. If you have any questions, please send me an email so that we can arrange an online recitation hour, okay? Online recitation or online office hour. Okay, then see you.
İyi akşamlar hocam, sağ olun.
Akşamlar. Furkan, beni zorladın bugün.
Estağfurullah hocam.
Kafam çalışmıyor. Hadi görüşürüz.
İyi akşamlar hocam.
İyi akşamlar.
Hoşçakalın hocam.
Görüşürüz. Belki sesinizi duymak ne güzel.
Hocam aslında bu tam sözlülük. UFD, PID.
Değil mi? Aynen öyle. Ben de düştüm. Baksana.
Çok karışık hocam. Yani bir şeyi anlıyorsun. Tam UFD falan diyorsun. Sonra PID'ler geliyor tekrar.
Aynen öyle. Ya çok şey. Şunlar benim kafamı o kadar çok karıştırıyor ki. Şimdi şu fonksiyonlar. Nerede çalıştık onları?
Hı hı.
Şu işte norm yaptık ya demin.
Hı hı.
Ha, bu fonksiyonlar mesela her ringin üstünde var. Sanki bu fonksiyon varken şeymiş gibi, direkt yüklediğin domainmiş gibi, her doğru istediğim zaman bölme yapabilirmişim gibime geliyor. Ama bir bakıyorum işte bazılarında tutuyor, bazılarında tutmuyor. Yani tutmaması demek de yüklediğin domain değil demek de değil. Yani başka fonksiyon vardır belki üstünde. O yüzden kafam çok karışıyor benim bunlar.
Ama çok güzel oldu hocam. Çok teşekkürler. Bayağı açıklayıcı oldu tekrardan.
İnşallah olmuştur. Ne diyeyim, kafanızı son bir 15 dakikadır karıştırıyorum. Çünkü benimki de çok karışık yani. Tam hiçbir zaman oturmadı. 30 yaşındayım çok şükür. Hala oturmadı. Bakacağız inşallah. Tamam, hemen koyayım o zaman bunu da siteye.
Evet.
Sizde sorunuz olursa bana sorarsınız.
Tamamdır hocam.
Tamam, hadi görüşürüz o zaman. İyi akşamlar.
Tamam hocam. Record bittiyse eğer.
Rekordu dur kapatayım. Olur. Nereden?